Welcome to Spring LIB.
Hi everyone. So what we're going to be doing in this problem is we're going to be using kinematics to relate the acceleration of this tractor shown here with the acceleration of this box shown here. And then we're going to be using Newton's second law and use that acceleration to find the tension force when SA has reached a certain number. So what we have given to us is we have a tractor that is moving to the right with a velocity of 4 meters per second and is accelerating at a rate of 3 meters per second squared. The tractor is pulling a rope which is attached to a load through a pulley, and we know that the total height of this pulley is 12 meters. The distance from the load to the tractor is defined as SA, and the distance from the ground to the load is defined as SB. What we're asked to solve for is the tension in the cable when SA is equal to 5 meters. So what we're going to be doing first is just doing some Pythagorean theorem to define the length of our rope in terms of SA and SB. So here's our rope, and here's the rope attached to the tractor, and here's our load. We know that this distance is SB, and we know that this distance from here to here is SA. We know that the total height of this pulley is 12 meters. We know that the total length of the rope, L, is equal to 24. Therefore, what we can do is we can rewrite L in terms of SA and SB. So we can say that L is going to be equal to 12 minus SB plus the square root of SA squared plus 144, which is just the length of this hypotenuse here, and that's this. So what we can do now is we can differentiate L here, which I'll rewrite as L is equal to 12 minus SB plus the square root of SA squared plus 144. What I can do is differentiate this length with respect to time and get velocity. So I can say that dl dt is going to be equal to 0 minus SB dot plus SA times SA dot all over the square root of SA squared plus 144. And this is equal to 0. Now we can go ahead and differentiate this again with respect to time to get acceleration. So we can say that the second derivative with respect to time gives us negative SB double dot minus SA times SA dot squared all over SA squared plus 144 raised to the 3/2 power plus SA dot squared all over the square root of SA squared, we get SA squared plus 144 plus S double dot A times SA all over the square root of SA squared plus 144. And this is equal to 0. Now, we see here that SB double dot is actually just the acceleration at point B. So we can rewrite this entire equation and say that AB, which is equal to the acceleration of SB double dot, is in fact just equal to the rest of that quantity, the rest of that equation, which is equal to SA squared, SA dot squared, all over SA squared plus 144 raised to the 3/2 plus SA dot squared all over the square root of SA squared plus 144 plus SA double dot SA all over, again, the square root of SA squared plus 144. Now, recall our initial information. We know that SA is equal to 5 meters, We know SA dot because that's equal to the velocity of the tractor. So SA dot is equal to 4 meters per second. And we also know SA double dot because that is the acceleration of the tractor, which is equal to 3 meters per second squared. So plugging all these known values in, we get an acceleration at B that's equal to 2.2 meters per second squared. Now we can use this acceleration and plug this acceleration into our Newton's second law for the load. Now when we draw the free body diagram of our load, we see that there's a weight force and we see that there's a tension force. So we can say that tension minus weight is equal to the net force in Y. We see that tension minus weight is equal to MAY. We can isolate tension and say that tension is equal to MAY plus W, which is just going to be equal to M times AY plus G. Now we know that our AY here is just equal to the AB that we previously calculated. Therefore, this gives us a tension that is equal to 1.8 kilonewtons, and that's our final answer.